Big Bang wasn't the start of everything, but just a moment in an endless cosmic cycle, a new theory called bouncing cosmology suggests the universe may alternate between phases of contraction and expansion, challenging the idea of a singular beginning. This concept could potentially explain some of the biggest mysteries in astrophysics, like the nature of dark matter and the formation of black holes, suggesting they may have formed before the Big Bang in a prior cosmic phase. Recent studies in the development of future gravitational wave observatories, such as LISA, aim to test these groundbreaking ideas, potentially revolutionizing our understanding of the universe. In this video, we'll explore what bouncing cosmology is, how it might provide a solution to the dark matter puzzle, and what future discoveries could mean for science. The bouncing cosmology theory presents a revolutionary perspective on the universe's origins and evolution. Unlike the traditional Big Bang theory, which posits a singular beginning followed by rapid inflation, the bouncing model suggests that the universe undergoes a cyclical process of contraction and expansion. This model posits that instead of emerging from nothing, the universe transitions from a phase of contraction, where it reaches an incredibly dense state, to a bounce that triggers the expansion we observe today. This concept fundamentally challenges the long-standing idea that the universe began with a single, unrepeatable event. To grasp the significance of this theory, it is essential to consider the limitations of the Big Bang model. While the Big Bang theory provides a robust explanation for the observable expansion of the universe and the cosmic microwave background, it leaves unresolved questions about the cause of the initial singularity and why the universe appears so uniform on large scales. Bouncing cosmology offers an alternative perspective by suggesting that the universe's current state is merely one phase in an infinite cycle. This idea bypasses the problematic beginning of time and implies that the laws of physics we observe today may be deeply influenced by conditions from a previous cosmic era. A crucial aspect of the bouncing cosmology theory is the concept of a non-singular bounce. At extremely high densities, quantum gravitational effects come into play, preventing the universe from collapsing into a singularity. Instead, these quantum effects cause a bounce, leading to a new phase of expansion marked by the emergence of photons and particles. Within this framework, what we traditionally refer to as the Big Bang is not the universe's beginning, but a transformation from a previous contraction phase to our current expanding universe. This cyclical model suggests that each cycle of contraction and expansion could influence the next. Pointing to a more interconnected universe across time, it implies that the seeds of galaxies, stars, and planets we observe today could have been laid down in a prior phase of the universe, shaping its evolution across successive cycles. Mathematical calculations and simulations support this model by predicting specific patterns in the distribution of cosmic structures, such as galaxies and the cosmic microwave background. One of the most exciting possibilities emerging from the bouncing cosmology model is the explanation it offers for the nature of dark matter, one of astrophysics' greatest mysteries. Primordial black holes, PBHs, proposed within this framework, present a potential solution. Dark matter, which constitutes about 80% of all matter in the universe, is inferred from its gravitational effects on visible matter and the cosmic microwave background. It does not emit, absorb, or reflect light, making it invisible and challenging to detect directly. Traditionally, dark matter was thought to be composed of exotic particles like WIMPs, weakly interacting massive particles. However, the bouncing cosmology model provides a compelling alternative. Dark matter could be made up of primordial black holes, formed during a previous contraction phase of the universe. During this phase, the universe would have been subject to extreme conditions of density and temperature. Under such circumstances, small fluctuations in density could lead to the formation of primordial black holes almost immediately after the bounce. when the universe transitioned from contraction to expansion. These black holes could have a wide range of masses, from tiny subatomic sizes to several times the mass of the Sun. What makes them particularly intriguing as dark matter candidates is their potential stability. If these primordial black holes exceed a certain mass threshold, they could survive the effects of Hawking radiation and persist to the present day, producing the gravitational effects observed in galaxies and galaxy clusters. The hypothesis that dark matter consists of primordial black holes is especially compelling because it bridges two significant areas of modern physics: cosmology and black hole physics. The existence of PBHs could explain why some regions of space exhibit strong gravitational pulls without any visible matter present, providing a new framework for understanding the universe's early conditions and linking them with events preceding the Big Bang. If future observations confirm that dark matter is composed of these ancient black holes, it would not only solve a major puzzle in physics, but also validate the bouncing cosmology model as a viable alternative to the standard Big Bang theory. This would suggest that the origins of both dark matter and the universe itself are more complex and interconnected than currently understood. Research in this area is already advancing, with scientists developing new models and simulations to better understand how primordial black holes could form and persist over billions of years. Researchers are also searching for indirect evidence of these black holes through their interactions with stars, gas clouds, and other cosmic structures. To confirm or refute the bouncing cosmology theory and its implications for dark matter, scientists need to detect specific types of evidence. One of the most promising methods is through the observation of gravitational waves, ripples in spacetime caused by massive cosmic events like the collision of black holes or neutron stars. According to the bouncing cosmology model, the formation of primordial black holes during a contraction phase would have generated a unique spectrum of gravitational waves, distinct from those predicted by standard cosmological models. Next-generation gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, and the Einstein Telescope, are being designed to detect these subtle signals. Unlike current ground-based observatories like LIGO and Virgo, which primarily detect high-frequency gravitational waves from relatively recent cosmic events, LISA and the Einstein Telescope will be sensitive to low-frequency waves. These low-frequency gravitational waves are believed to have originated from much earlier in the universe's history, potentially dating back to the time of the bounce itself. Detecting these specific gravitational waves would be transformative. It would provide direct observational evidence supporting the bouncing cosmology model and the existence of primordial black holes as dark matter. If these waves exhibit the patterns predicted by bouncing cosmology, it would challenge the inflationary paradigm and offer a new understanding of the universe's structure and origins. Such discoveries would not only validate the bouncing model, but also redefine the fundamental principles of cosmology, potentially merging quantum mechanics and general relativity in ways that current models do not fully account for. Moreover, the search for these gravitational waves is already underway. Scientists are analyzing data from existing gravitational wave detectors for any signs of these primordial signals. While some interesting candidates have been identified, more data and more sensitive instruments are required to confirm these findings.